Okay, good morning everyone. So my talk today is about homogenization of GNSS integrated water vapor time series and estimation of climatic trends. There will be a small update of the presentation I gave at the EGU in Vienna. This work is mainly the contribution of Nîmes and Guyenne, who did her PhD with Olivier and myself. Okay, so there is high interest in long-term, high-quality GNSS integrated water vapor data for monitoring climate change and variability, verifying atmospheric reanalyses and climate models, and also for bias-correcting model simulations and satellite observations. On the top right plot, you can see IWV yearly mean anomalies, global average over land. From three reanalyses, ground-based GNSS in red and GPS radio occultation in blue. There is strong interannual variability, especially due to El Niño events, superposed with a clear trend about 0.4 kilograms per square meter per decade. However, there are some discrepancies between the reanalyses and the observations. And on the plot on the bottom, we can see the regional distribution of trends in percentage per decade, sorry. And the values clearly go up to 5 to 6% per decade, but some regions in positive and some regions have also negative trends. So there is a large regional variability in the trends, and it's very useful to have GNSS observations to validate reanalyses and climate models, as I said. So the background on that map is from era 5, and the dots are from GPS observations. So the accuracy goals we're looking for are about 0.5 kilograms per square meter in absolute value for IWV, and the trends more about 0.2 kilograms per square meter per decade, or 1% per decade. There are biases and bias changes which cause inhomogeneities in the GNSS series, which are at the level of 0.5 to 1 kilogram per square meter. So this is really the main issue. And they are due to changes in the processing, in the equipment, and changes in observation conditions. So there are two main ways to improve the homogeneity of this GNSS series. The first one is at the observation processing level. The second one is post-processing, which is known as homogenization, and this is really the purpose of my talk today. So we have developed a homogenization procedure. It is based on three main steps. The first one is segmentation, and then there is attribution and correction. So the right part of the slide shows the segmentation. The goal of the segmentation is to detect the change points, the position of the change points, and the number of change points are unknown. Our method works on IWV differences. The GNSS series are different with respect to a reference. For that we use era 5 reanalysis for now. And the model for the time series, which is shown, time series is shown on the plot here. The model is the constant mean, piecewise constant mean, superposed with a periodic bias, which represents difference in representativity between the observation and the reanalysis, and also time-varying noise variance. So all the parameters of this model are estimated by penalized maximum likelihood method, which is an optimal method. And so the number of changes, the position of the changes, the means, the periodic bias, and monthly variance. So this approach is very efficient at detecting change points. However, we work on a different series, so the change point might be due to GNSS or the reanalysis. We cannot assume the reanalysis is homogeneous. So that's the goal of the attribution. The attribution will decide whether the change point is due to GPS or to the reanalysis, so G or E. It works by introducing nearby stations. So for each nearby station, we have two series, a GPS series and a reference era series, so G prime and E prime. So we have 4 series. We form 6 series of differences, which which are shown in the plots, and we test if the mean is changing significantly from the left to the right, so before and after the change points, which was detected in the main station. And on this example, you can see that there is a clear downward shift at the change point in the first three series on the left column. So these three series involve the GPS series, and the three series on the right have no significant change point. So we have 0 for the test results, -1, which is significant downward for the formal 3. And from the 6 test results, we go to the logical table. And from the logical table, we can get back to what we call here the truth, which is the change attributed to one of the 4 series which we used in the test. So this is a prediction. Of course, the test may fail because in some series we have noise. So sometimes the 6 test results will not be in the table, and we need to use a probabilistic approach to make the prediction. So we use a machine learning classifier, which we trained on our data set. So we developed and tested this segmentation and attribution methods on different data sets. The first one was the IGS Repro 1 Tropo solution. Second one was the Code Repro 2 solution. And we extended, because we need nearby stations, we extended the Repro 2 from Code with NGL Repro 3. So it brought several nearby stations. And more recently, we used NGL Repro 3, which has about 20,000 stations worldwide, and we analyzed 6,000 stations, which are more than 10 years of data. And this allowed us to train the classifier with more than 30,000 cases. The map shows the density of the stations in this data set. So coming to the results, we found very consistent segmentation results from the 3 data sets I mentioned. On average, the number of change points is between 1.5 to 1.7 every 10 years. However, 10% of the stations were homogeneous, so no change point was detected. And with the IGS stations, so JPL and Code solutions, we found that more than 30% of the detections could be validated with metadata, so from the log files. Mainly antenna and radon changes, and some receiver and some cutoff changes. With NGL, we could not validate so many breaks, change points, because they were lacking metadata. But the 2 plots on the bottom show the size of the offsets, which on average are about 0.4 kilogram per square meter, so it's quite important, quite large. And the plot on the right shows the signal-to-noise ratio of these detected change points compared to the background noise. And the mean SNR is about 0.7, which shows that our detection method is very efficient, because such a low SNR would be very challenging for classical test methods. Okay, here are the attribution results. I'm showing here for 2 of the data sets, the Code Repro 2 and NGL Repro 3. So the number of stations is different, of course. The number of change points is more or less consistent. And we find that about 60% of the change points could be attributed to GNSS. So double compared to what we could decide from the metadata only. And between 20 and 30% to the reanalyses, which we have to confirm, of course. We don't have many metadata for the reanalysis, but this is still possible. And we would expect that a jump in the reanalysis at one place would also be detected at another place. So having a large number of jumps in E and E prime makes sense. Okay, now what is the impact of detecting and correcting the jumps on the trend estimates? We show here the results for NGL Repro 3 only. There were 600 stations which had 20 years of time series. About the 600, 410 could be fully homogenized because we had nearby stations. And the statistics here show that, okay, we compare the trends from era 5, GPS low, so before homogenization, GPS homogenized. On average, there is not a big impact, but if we look at specific stations, I will show an example just after, the impact can be quite large. So after homogenization, the GNSS trends get closer to era 5, which makes sense, but era 5 is not completely independent here. And we see that the number of significant trends is slightly increasing after homogenization. So these are 3 examples with quite large jumps. So, and the impact on the trends is shown at the bottom. And okay, so here is missing, information is missing on the attributes of the changes. But if I remember well, on the first example, okay, here. In this case, you see there are 3 changes detected. They are all 3 due to GNSS. In the second case, there are, in the second case here, the bigger changes are due to GNSS, and one of the changes is due to GNSS and error. And in the third case, there is also a mix of GNSS and error. The impact on the trend is quite large. Of course, in the first case, there would be, if we estimate the trend, we would expect a positive trend in the GNSS series, and which you see in the value below the plot. After homogenization, the trends on all 3 stations come consistent, which makes sense. Okay, so coming to the conclusions, mainly the results, okay, I will not repeat the summary. The 2 first points are just the summary. I want to advertise that we have R packages which implement the method. The GNSS segmentation, we have 2 versions. The first version called GNSS seg, and then we developed a fast version based on the pruned dynamic programming method, so we would recommend to use that one. The attribution method is available, it's a beta release for now, but we are finalizing it, and the next step will be a full homogenization package which implements also the correction. Okay, if you are interested in using these packages, you can contact me. And I would just like to advertise for the next step. This is homogenization as post-processing. We plan now to work also on the processing aspect, because we know that some of the jumps are connected to equipment changes and also to changes in cutoff angle. And it's an interesting way to try to improve the accuracy, absolute accuracy and homogeneity of the series by tuning the processing, which may be station dependent, because atmospheric variability and noise aspects are highly station dependent. We have a splinter meeting today, so I'm advertising for people interested in tropospheric analysis and applications at 4 p.m. in room B78, so downstairs. And we will also present some of the objectives of this work tomorrow in the tropo session. And this work is developed in the framework of a joint working group of AAG, which is referred. Okay, so thank you for your attention.